Statistics isn't just about a bunch of numbers in a textbook. It's really a toolkit, a guide for making sense of reality. In a world that's just full of noise, it's how you find the signal. So let's break down how you can actually use it.
In today's world, we're absolutely flooded with data, right? So being able to tell the difference between solid reasoning and, well, faulty reasoning is basically a superpower. And that's the bottom line, isn't it? It's about being informed versus being manipulated.
Okay, so the big question is, how do you actually do that? How do you spot the truth when you feel like you're drowning in numbers? You need a reliable set of tools to react intelligently to all the information we're bombarded with every single day. Let's build that toolkit.
All right, so let's get into it. The very first tool in our new toolkit is all about taking a big, chaotic mess of information and just simply describing what we see.
So, you can basically think of statistics as having two main jobs. Over on the right, you've got inferential statistics. That's the fancy stuff, trying to generalize or predict what might happen in a larger group. But you can't predict anything if you don't even understand what's happening right now. And that's where descriptive statistics comes in. It's all about summarizing the data you have right in front of you. No guessing, just clearly describing the world you can see.
Okay, so check this out. Imagine we've got this table of salaries from some data set. I mean, the information is there, sure, but it's just a list of numbers. Your brain has to work pretty hard to quickly grasp the scale of the differences, to really feel the gap between them. But then, boom, look at this. The second we turn that table into a simple bar chart, the story just jumps out at you. You don't have to think, you just see it. You can immediately feel the scale of those salary differences. That right there is the power of good descriptive stats.
You know, our brains are basically pattern-finding machines. We're just wired to see connections everywhere. The tricky part is, are those patterns real, or are we just seeing things? Statistics helps us sort out the real connections from, well, just random noise.
Here's a great example. If you look at the ages of married couples, you'll find what's called a strong positive correlation. All that really means is that as one person's age goes up, their partner's age tends to go up too. Pretty simple, right? Older folks tend to marry older folks. It's a very consistent pattern. But, and this is maybe the single most important rule in all of statistics, you have to burn this into your brain. Correlation does not mean causation. Just because two things happen to move together doesn't mean one is causing the other to happen.
This is a perfect example of something called the third variable problem. There's this famous case from Taiwan back in the 70s. The data showed that families who owned electrical appliances were also more likely to use contraception. So, do toasters cause family planning? Of course not. The real driver, the hidden third variable, was education level. More educated people were more likely to do both.
Okay, so if we can't just trust correlation to prove that one thing causes another, how do scientists ever prove anything? How do we get from just noticing something to actually making a solid conclusion? Well, we can use a really powerful formal process for this. It's called hypothesis testing, and it gives us a step-by-step structured way to evaluate whether an idea is actually supported by the evidence. Think of it like being a detective. You follow 4 key steps. It's a system for figuring out if what you're seeing is the real deal or if it could have just happened by random chance. So here's how it starts. You set up 2 competing ideas. The first one is called the null hypothesis. That's the default, skeptical position. It basically says, nope, nothing's going on here, no association. Then you have the alternative hypothesis. That's your theory, the idea you actually think is happening, that there is a real connection.
And this leads us to the famous and sometimes infamous p-value. The best way to think about a p-value is as a coincidence detector. It asks a very specific question. If the skeptical null hypothesis is actually true and there's no real effect, what's the probability we'd see results like the ones we got just from random luck? A tiny p-value means it would be a massive coincidence.
Now, in most of science, the unofficial rule, the line in the sand, is a p-value of less than 0.05. What does that mean? It means there's less than a 5% or a 1 in 20 chance of seeing your results if it was all just a random fluke.
So let's go back to our coffee versus energy drink example. Imagine we run the numbers and our p-value comes out to 0.04. Well, that's less than our 0.05 threshold, so we get to reject the null hypothesis. In plain English, that means the connection we saw between gender and drink choice probably isn't just random. But hold on, even with this really careful process, we're still just talking about probabilities, not absolute certainties. And that means there's always a risk that we could get it wrong, in one of 2 specific ways.
And this table lays it out perfectly. Look, if there's no real effect out there but our test flags one anyway, that's a type 1 error. It's a false positive. Basically, a false alarm. On the flip side, if there is a real effect, but our test is blind to it and misses it completely, that's a type 2 error, a false negative, a missed opportunity for discovery.
Okay, so let's wrap this all up. When you put these pieces together, you've basically built yourself a powerful new toolkit for becoming a real data detective.
So, what's in your toolkit? 3 key skills. First, you know how to describe data, to see what's really there. Second, you know how to spot correlations, but you're always on the lookout for that causation trap. And third, you know how to test an idea, to see if it's the real deal or just noise.
And that, right there, is why any of this matters. Because now you're equipped to be a smarter, more critical thinker. You won't be so easily manipulated by flashy headlines or dodgy stats. The next time you see a big claim, you can ask the right questions. Are they just describing something? Is this just a correlation? Or have they actually tested it? And that is the power of statistical thinking.